Hi everybody. As promised, I'm going to go through sort of an alternate derivation of the recursion relation for the Legendre equation, and I'll focus on the case s equals 0. The case s equals 1 is very similar. In fact, a sub 1, the only trick there is that a sub 1 is equal to 0 as well, but the terms are kind of mixed up. You have a sub 0, a sub 2, a sub 4, but they're attached to odd powers of x. That's why we call it the odd series of Legendre equation. So let me write the Legendre equation in a slightly different way. I'm just going to multiply -1 through everything. And again, this is for s equals 0. And we're looking at our Frobenius expansion. So we have 1 minus x times the sum. These are going to be all sums over j. J times j minus 1 times a sub j times x to the j minus 2. It's the first term. Minus 2x times the sum over j of a sub j x to the j minus 1 plus lambda times the sum of a sub j x sub j equals 0. The only difference here is I just, for convenience sake, multiplied that -1 through. Now let's break apart these terms again like I did to set up the class. Namely, we have the sum over j of j times j minus 1 times aj times x to the j minus 2 minus the sum of j times j minus 1 aj x to the j minus 2x times the sum over times j, all right, j here, times j of aj x to the j minus 1 plus lambda times the sum over j of a sub j x to the j equals 0. Okay, further simplifying this, we have the sum over j of j times j minus 1 aj x to the j minus 2 minus the sum over j of j times j minus 1 a sub j x to the j minus 2 times the sum over j, bringing the x in now, times j times a sub j times x to the j plus lambda times the sum over j of a sub j times x to the j equals 0. Okay, now the only tricky part here, and that's quite useful, is recognizing that we can reindex all of this. So we're going to reindex some of these functions. In particular, we're going to look at this j to the minus 2 term. And we're going to reindex it so that we are looking at adding j plus 2. Right? And in fact, we're basically we're starting, instead of with j's, we're replacing with j plus 2, which we can do with complete generality if we're starting from j equals 0 and moving forward. And we haven't terminated the series yet. So this becomes the sum then of j plus 2, that is, we're just replacing j with j plus 2, times j plus 1, we're replacing this with j plus 1. This is a sub j plus 2, and now it may become obvious why we did this. We've recast x to the j minus 2 with xj. Okay, now we have the sum of j times j minus 1, a sub j x to the j minus 2 times the sum of a sub j x to the j plus lambda times the sum a sub j x to the j all equals 0. This neat little trick means that all of our coefficients are multiplying the same power of x, that is x to the j. Right? All we did was shift that meaning of j so that we could be looking at the coefficients that are multiplying those powers. That means that the sum of j plus 1 times j plus 2 times aj plus 2 plus a minus j times j plus 1 plus lambda times aj all has to be equal to 0, right? Which means that in general j plus 1 times j plus 2 times aj plus 2 plus a minus j plus 1 plus lambda times aj is equal to 0, or a sub j2 is equal to j times j plus 1 minus lambda over j plus 1 j plus 2 a sub j. So this is an alternate way. We now have our recursion relation. The reason why we might want to do it the way that we've done in class is if we just want a couple of terms and we can read those out pretty quickly from a table, or if we want to quickly identify how a series might be written in terms of a sub 0. But we have the same problem here, that namely for the Legendre equation, the series expansion diverges at the endpoints. And so in order to make this work, we need to terminate the series so that it's no longer an infinite series. Terminate it such that sum j equal to L means that lambda is equal to L times L plus 1. And when we do that, we see that a sub L plus 2 for that value is equal to 0. And we end up with a sub j plus 2 is equal to j times j plus 1 minus L times L plus 1 over j plus 1 times j plus 2. Since in this case s is equal to 0, our sum of a sub j x to the j means that we're looking at even powers of x, because in our solution up here, we had basically, if you look, a1 is equal to 0, so only even a2 or a sub j's survive. Okay. Now, when it comes to the other root of the indicial equation, s equals 1, we can do the same, the exact same argument. Okay? And what we'll find for that is that ultimately a sub j plus 2 is equal to j plus 2 times j plus 1 minus lambda over j plus 2 times j plus 3 times a sub j. And again, this is divergent, so in order to make this converge, we terminate the series at a j equal to L such that lambda is equal to j plus 2 times j plus 1. Again, because the only things that survive are even values, right? A1 here is also equal to 0, right? We know that this series terminates at this value, but here the solution is going to be a times, x to the j plus 1, and that's because our indecisional solution has s equals plus 1. Since j is even, this will represent the odd series for the Legendre polynomials. So what this gives us, if we normalize things properly in the way that you expect, is that you would get the P1, P2, P0, etc. from, for example, E and M and the solution to Laplace's equation. What we have done here is shown that we have been able to identify the eigenvalue lambda in terms of discrete values, in particular integer values of L. And even though it doesn't quite look like this, you should convince yourself that this is going to represent the same eigenvalue. Namely, this is just shifted off by a factor of 1, right? Since s is equal to 1. And so the whole result of this kind of analysis is that this operation, right, gives us this with L times L plus 1, right? Where we've identified what L is equal to, okay? And this is true for our self-adjoint ordinary differential equations. And often what is important here is what's the eigenvalue. It's also important to know what the eigenfunction is, but often since the eigenvalue is what we want, what we're trying to observe, that's the thing that's of importance. So for your homework, you have, I believe, the Legendre equation, and that's 8.3.4, and I want you to follow the similar analysis. You can either use this general method or you can use the method that we used in class in order to identify the indicial equation, step 1. Step 2, see if you can find the pattern in a sub 4, a sub 2, a sub 0, and either from induction or from a general argument, find the recursion relation. Now, fortunately, I believe your book gives you the recursion relation. You certainly can look it up and sort of aim for that. Using mathematical induction is a bit of an art form. So if you need any help, make sure you contact me. You guys did really great today. This was kind of an experiment. And again, if you have any questions, make sure you give me a ping and I'll be here. Okay? All right. See you Friday.